Okay, I can see that most of the audience is there. Let me start with introducing our speakers today. Our first speaker will be Hamed Kastet. He's the head of innovation at Birdz. You might be familiar, you're probably familiar with Veolia, one of the largest utilities worldwide, and Birdz is responsible for most of their advanced metering deployments. So there is a ton of experience with Hamed, and he will be really going through the details of both wireless M-Bus and OMS. Then we'll have Palle Haderslev. He's been dealing with OMS for many, many years and specializing in really the OMS middleware and the decoding. So you will get a bit more details on how to practically deal with the OMS protocol. You'll see some examples. And then even more practical, if you want to go into designing a meter that supports wireless M-Bus, supports OMS, supports LoRaWAN, you will need a stack. And I think everyone in the LoRaWAN world is familiar with Stackforce. And Conrad Aisha will go through the add-ons to the well-known LoRaWAN Stackforce stack that is also dealing with wireless M-Bus and OMS. And besides the introduction, I will also do wrap-up rapidly. So regarding the agenda, we will go first really to introducing M-Bus, OMS, the exchanges, the flows, the frames. Then, so this will be Hamed. Then Palle will go to real demos and explain how you can introduce a decoding stack in your LoRaWAN core network. Then Stackforce really will explain how to practically integrate. And I will wrap up by going through also some of the new stuff around metering, relay, drive-by, and how all of this integrates in a seamless metering framework. With that, I'm happy to introduce Hamed, and let's go to a deep dive.
Hello, everyone. Thank you, Olivier, for the presentation. So today I'm going to present you the OMS Over LoRaWAN solution. This solution was developed in a joint technical task force between the LoRa Alliance and the OMS group. And this solution is combining the performance of LoRaWAN with the interoperability provided by the OMS specification based on the M-Bus standard. So next slide, please, Chansey. First of all, you have already heard about M-Bus and wireless M-Bus, but it is still maybe a bit confusing for a lot of people. So first of all, M-Bus is a European standard described in the EN 13757 series. So it was developed initially for the wired communication back in 1993, and it was then improved to be compatible with radio solutions, and this is why we had the emergence of the wireless M-Bus protocol. So M-Bus and wireless M-Bus are designed for the meter reading of water, gas, heat, and electricity meters. And the wireless M-Bus has different radio modes in different frequency bands like 868 megahertz and 169 megahertz bands. And it is based on FSK radio modulation. And those radio modes are described in the EN 13757-4 document, and it was first introduced in 2002. Next slide, please. So the wireless M-Bus standard had a lot of features that could be used by meter manufacturers and utilities to collect data from the field. So first of all, the advantage of M-Bus is the generic and flexible application layer and data representation, in which every data aspect coming from the meter could be represented in a standard manner, so it could be decoded and interpreted correctly on the backend system. It is a bidirectional radio protocol, so in a way that the gateway and server could interact and send commands to the meter. And it has a strong built-in solution for the cybersecurity aspect. So all the required property in terms of cybersecurity, like confidentiality and authentication, are provided. And it has also a mechanism for the key update. It also deals with fragmentation for long messages, and it supports as well the clock synchronization and the firmware update over the air. Next slide, please, Chansey. Yes, so the M-Bus standard is being used by the OMS group to develop specifications. So first of all, what is M-Bus? M-Bus is a European association that based in Germany and founded in 2015. So it includes all the smart metering value chain actors like meter manufacturers and utility and service providers. So as I said, the OMS group has different working groups dealing with the OMS specifications based on the M-Bus standard. And those specifications are intended to promote the interoperability by reducing the standards in the M-Bus standards options. And with this, the OMS is also providing the certification to ensure the reliability of the products. And since 2020, LoRa Alliance and the OMS group had a joint technical task force to promote the usage of OMS over LoRaWAN based on the technical report number 6, OMS over LoRaWAN, that is using the M-Bus Adaptation Layer that has been defined in the EN 13757-8 document. So next slide, please. So as you see, the OMS group had a lot of members who can recognize the main and the major meter manufacturers and the service providers that are dealing with the smart metering industry, which provide a large ecosystem of manufacturers and solution providers in the OMS group. Next slide, please. So here we can see the device types that the OMS certification committee is dealing with. So we have more than 93 certified products that are available on the OMS group website. Those products are mainly meters like gas, water, and heat meters, but we have also sensors like smoke detectors and pressure devices as well. Next slide, please. So here we have a focus on the M-Bus security mode versus the OMS security profiles. So as I said, the OMS specifications are based on the M-Bus standard. And we see on the right that OMS provides multiple security profiles, and each of those security profiles are defined based on the M-Bus security modes that we see on the left side from the table from the EN 137-7 document. So you see that security profile A is based on security mode 5, and security profile B is based on security mode 7 from M-Bus. And as well, security profile D is based on the M-Bus security mode 10. So those are the profiles from OMS, but you see also the security profile C that is based on the security mode 13, which is not defined in the M-Bus standard because it uses the TLS security protocol to convey the data from the meter to the gateway. Next slide, please. So here we have a comparison of both LoRaWAN and wireless M-Bus according to different technical and operational metrics. So let's start with the first three technical metrics. So as I explained before, the FSK, the wireless M-Bus is based on FSK modulation, and this FSK modulation has a high data rate, which leads to a short range communication, but it enables at the same time a very low power consumption and a large payload size. While LoRaWAN features lower data rates, enabling a longer range with an affordable power consumption and suitable payload size for metering applications. But one of the major differentiators between LoRaWAN and wireless M-Bus is the standardization of the application layer. So the M-Bus payloads are specified in the EN 13757-3 document, whereas the LoRaWAN deals mainly with the physical and the link layer. So, and another element that distinguishes them is the possibility to use public radio network infrastructures. So wireless M-Bus radio gateways should be deployed in private mode, while in LoRaWAN, we have major European telecommunication operators that provide nationwide LoRaWAN coverage. So both technologies have quite a good ecosystem of manufacturers and providers, but LoRaWAN has a definitely wider and stronger ecosystem thanks to the LoRa Alliance, and the OMS has a leading and a reference position in the smart metering applications, especially in Europe. Next slide, please. So to summarize this analysis, we could say that currently we have two separate approaches. Wireless M-Bus in 868 MHz band does not provide long-range radio to tackle deep indoor conditions, while LoRaWAN's radio provides long-range communication, but it is application agnostic. So therefore, utilities should develop new interfaces to cope with proprietary payloads, encoding and decoding formats. So given the situation, the idea is to bring wireless M-Bus and LoRaWAN together because they complement each other. So LoRaWAN will benefit from M-Bus application layer standardization, while M-Bus and OMS will benefit from the LoRaWAN's radio performances and networks deployments. So in the next slide, please, we're gonna see the benefits of using this new mechanism, which is OMS over LoRaWAN. So when using OMS over LoRaWAN, the utilities will be freed from the burden of deploying and maintaining radio networks because they can leverage and benefit from the nationwide network coverage deployments, and we have also the possibilities to have a cooperation between nationwide coverage and private networks. And on top of that, we have the roaming feature in the LoRaWAN networks that enable the extension of the coverage while providing an affordable cost for that. And along with this performance and operational aspect, we have also the interoperability. So with OMS application layer, there will be no change of the utilities legacy M-Bus head-end systems and applications. So the M-Bus and OMS application format will be conveyed on top of LoRaWAN, so the servers will not need to change anything to decode and to process the data coming on the OMS over LoRaWAN messages. And with that, we have an access to a wide and advanced ecosystem of hardware and software solutions, so dedicated to smart metering, because both OMS and LoRaWAN ecosystems includes a variety of meter manufacturers and utilities dealing with and using the OMS and the LoRaWAN protocol. With that, we have also the access to an open source reference protocol stack implementation of LoRaWAN, and we have also the certification mechanism both for OMS application and for radio in the LoRaWAN protocol. And with the LoRaWAN as well, the application providers or the meter manufacturers could access to worldwide radio regions with the LoRaWAN protocol, which we do not have really in OMS because it is focused on the European 868 megahertz band. Next slide, please. So now we will take a look on the M-Bus Over LoRaWAN protocol stack. So you see on the left the OSI model layers, the standard reference model for the network communication. And on the second column from the left, you see the M-Bus layers. So we have on top, we have the application layer, and then we have the transport layer and the authentication and fragmentation layer. And down we have the data link layer and the physical layer. And between the what we call the upper layers and the lower layers, we have the adaptation layer. And the adaptation layer is a mechanism that has been recently defined in the EN 13757-8 document to enable the transport of the M-Bus upper layer, so mainly the application and the transport layer, on top of LoRaWAN in a standard and interoperable solution. Next slide, please. So as I said, here we have a look on the wireless M-Bus messages mapping to LoRaWAN F port. So in the M-Bus protocol, we have different message types that we call services, and those message types have a dedicated meaning and function for the meter and for the head-end system, for the application server. So in order to keep the correspondence and the mapping of those the messages on the meter and the head-end system, every message type has been allocated to a dedicated F port from the LoRaWAN frame in order to distinguish and in order to process correctly the M-Bus messages. So for instance, we have the installation messages, we have the application data in uplink and downlink, and we have messages dedicated to alarm indication and to alarm requests. And also we have some acknowledgement that are expected on the and handled by the M-Bus transport layer. And all of this has been done in the M-Bus adaptation layer that we will see in the next slide, please, Jancy. So here we have the frame format of the M-Bus and OMS over LoRaWAN. So this is achieved by using the M-Bus adaptation layer, in which the M-Bus, the MBAL control field is located in the F port of LoRaWAN. So F port transport the MBAL control field, and this field contains the M-Bus frame type, the messages that we described previously, and it carries as well the M-Bus application accessibility in terms of accessibility in bidirectional way, and managing the end devices latency when it comes to answer the downlinks. And along with that, we have a separated acknowledgement mechanism, one from the LoRaWAN network and another from the application that is managed by the transport layer. And it is very easy to achieve this mechanism because the M-Bus payload that contains the transport and the application layer fields are simply included in the frame payload from LoRaWAN. And with this manner, the hidden system or the meter application layer could extract the M-Bus payload, application and transport layer payload, from the LoRaWAN frame payload, and it could be able to process this payload in as it was done in the M-Bus and wireless M-Bus, and the frame port provide the information about the frame type and about the fields that we have in the M-Bus adaptation layer control field that we described before. Next slide, please. So here we see an example of the installation procedure for the M-Bus over LoRaWAN. So first, you see that on the left, we have the end device, and we have the end device upper layers, mainly the application and the transport layer, and we have the end device LoRaWAN, let's say LoRaWAN protocol running on the end device. On the middle, we have the LoRaWAN network, and on the right, we have the head-end system and the application layer of the head-end system. So first of all, the end device starts by joining the LoRaWAN networks by sending the join request, and then the network will send the join accept. And once the join accept message has been received, the application layer of the end device will send the installation request from the end device to the head-end system using the dedicated F-port value 22 and using the long TPL header, which contains the address of the meter, so it could be mapped in the head-end system with the LoRaWAN dev UI and device address. Once this installation request is received in the head-end system, this one will send the confirmation of the installation request using the same F-port. And once the confirmation is received in the end device, the status of this one is switched to installed, and then it can start sending the application traffic using the send no reply message using the F-port number 20. Another example is provided in the next slide as well, please, Chancy. So next slide, here we have a mechanism where we can send the data from the head-end system to the end device. So the head-end system needs to update the user data on the end device, and then it will queue the request user data to message in the LoRaWAN network server. And using the frame port number 43 that we described earlier. And once the end device sends the send no reply message, the periodic uplink message using frame port number 20, the network server will convey the request user data to message in downlink to the end device, and then the end device will answer this message using the response UD message, the response user data, using the dedicated F-port as well. And here the end device will use the confirmed mode of LoRaWAN to be sure that the message has been delivered. So once this message, the response UD message, is delivered to the network, this one will be forwarded to the head-end system, and the LoRaWAN network will send back the LoRaWAN acknowledgement to the end device. So this was an overview of the different mechanisms that we have in OMS over LoRaWAN. So More of those mechanisms are described in the technical report number 6 that is publicly available on the OMS website. So, and I encourage you to download this technical report. It is very clear and easy to understand, and it provides frame examples and different figures to explain this OMS over LoRaWAN mechanism. Next slide, please. So this slide just to talk about the company I'm working for. So as Olivier mentioned in the introduction, so I'm working for Birdz. Birdz is a 100% subsidiary of Veolia, and we are focused on water, waste, and energy services. So we have been founded in 2017, and we are more than 170 employees based in France, and we have more than 25 years of experience in smart metering, and we are operating more than now more than 4 million devices and deploying networks in more than 3,300 municipalities across France and Europe. And if you need any more information about the OMS over LoRaWAN mechanism and solutions that are provided by Birdz, don't hesitate to look at the Birdz website. With this, I want to thank you for your attention. And now I will switch to Palle, who will give us more details about real deployments and real usage of OMS over LoRaWAN in the solution.
Thank you, Ahmed. That's great. Hello, everyone. My name is Palle Haderslev. I'm from Device Lab. And well, I'm grateful for this opportunity to share some of the work we're doing at Device Lab. But who is Device Lab anyway? Well, briefly explained, we are a rather small team specialized in software to decrypt and decode OMS payloads and nothing else. So we're definitely filling out a niche. I would say even calling us a bit nerdy. But why is Device Lab a rarely seen bird in the LoRaWAN ecosystem? What has changed? Well, what has changed is the Technical Report 06, which was issued in 22, specifying how to embed an OMS payload into a LoRaWAN datagram. And that has made our server software for decoding OMS payloads relevant here as well. And now, these days, more and more OMS-compliant LoRaWAN meters are being released to the market. That has changed. So in essence, at Device Lab, we don't really mind what technology is being used to carry the payload. As long as the payload is OMS-compliant, our software will decode it. The OMS specification, as mentioned by Ahmed, is, and the technical reports, of course, are freely available from the OMS website. But I won't lie to you. If you add the EN 13757 wireless M-Bus specification, it's nearly a pile of 1,800 pages, and they are no easy read. Maybe for Ahmed, but he's an exception. And that's why Device Lab has devoted our efforts to this. And trust me, we still find surprises, both in the specification documents, but also in the interpretations done by the various meter manufacturers. Next slide, please. Yeah, let's talk about metering, which is our main focus at Device Lab. It all starts with a meter. It's broadcasting encrypted and encoded datagrams, and it ends up as data or readings in some sort of front-end application, whether it's for energy, utility, or property management purposes, or completely different purposes. But to close the gap between the two parts of the chain, the incoming datagrams need to be decrypted and decoded, and you could say translated into a readable format, like, for instance, JSON or XML if you prefer. That is the output then is very easy for you to store in your main meter reading database. So you could put it briefly to sum up what's being encoded and encrypted, for instance, by Stackforce, which you will learn about more later. It has to be decrypted and decoded in order to be useful. Next slide, please. Well, let's take a look into the technical report 06, already mentioned. The shown diagram explains how the OMS support is achieved in a LoRaWAN system. In essence, all gateways must be capable of collecting datagrams from any sort of device, whether it's OMS compliant or any other, and forward them to the network server. The network server then distributes the payloads to either the OMS application server or to the normal application server, and from here onwards to the different headends. Next slide, please. Right. A noteworthy difference is that where LoRaWAN is intended for a wide range of IoT use cases, OMS is intended for metering only. So although also specified for as bidirectional, it's almost always unidirectional or end-device broadcasting. So where the end device addresses containing each and every datagram transmitted by the wireless M-Bus meter, the address is only transmitted with the installation request for the LoRaWAN meters. Hence, the address has to be stored and added to the decoding requests. Next slide, please. And here I've taken a snap from a rather long and rather complex table taken from the OMS specification, here covering cold water meter volume readings. As you can see in the table, the data points encryption is mandatory. That's a huge difference from wireless M-Bus standard. And some of the data points are mandatory, and whereas others are optional or conditional. That's up to the manufacturer to decide. All OMS compliant cold water meters must follow this specification in order to be OMS compliant. Hence, here from the interoperability. So you can, in essence, you can replace an OMS compliant cold water meter from one meter manufacturer with another one. And this table in the specification covering all sorts of meters like heat meters, cooling meters, water meters, gas meters, electricity, and even some sensors. Next slide, please. Another extract from the OMS Technical Report, now on security. In fact, Ahmed already touched the security profiles. So I would just like to add that there is a selection of security profiles which you can choose, going from no security profile, where the security is handled by the LoRaWAN protocol, or you can choose the security profile A, B, C, or D, whereas, of course, the A should not be used. That's not recommended for new designs. Security profile is the main used. And C is rarely used because that's for bidirectional uses, and that's not normally the case in metering. And the security profile D is, in essence, an optimized version of security profile B. Next slide, please. Now, let's get some hands-on now. Taking a look at our laptop version, you can see the incoming datagram to the right, inserted with red, exactly as it was transmitted by the meter. It has just been collected and forwarded by the gateway. The parsed output is shown in the middle, in this case as a JSON file, or at least part of the JSON file. And our server software does exactly the same thing, just without the user interface. Next slide, please. And now, how does this look when implemented in the ThingPark platform Actility? Actility will kindly provide me with some screenshots, but by no means I'm a ThingPark expert at all. But firstly, you can see, as an example, you can see the meter master data from a Comstock Flow IQ 2200 cold water meter is shown here, and including the OMS key, which is stored in the DEC tag. Next slide, please. And here you can see the meter communication log which is providing communication specifics like radio parameters and timestamps, so you can actually monitor the datagram which is being received from the end device. The next slide, please. And finally, the resulting JSON shown in the trace tool. You'll recognize the JSON file format from the previous example from our own software, but I'm quite confident that Olivier can provide much more insight than me on the ThingPark implementation details. Specifically, I'm interested to hear how long it took to implement it, but I'll leave that to Olivier to state. The last slide, please. Yeah, that's the unavoidable page that has been forced upon me by our marketing. I won't bother you with the details. I would just like to emphasize that the fact that our software also supports the what we call near OMS datagram, which is transmitted by the LoRaWAN meter modules from Melvaco, which is used by major meter manufacturers like Kamstrup, Diehl, Landis+Gyr, Engelmann, and Itron. Yeah, I would like to say thank you for your patience, and now over to Conrad.
For handing over the presentation to me. Also from my side, welcome to today's webinar. My name is Conrad Reicher, and I'm the Commercial Managing Director of Stackforce. The next about 10 minutes, I will present you the solution from Stackforce for OMS over LoRaWAN, a scalable and interoperable IoT communication technology. Beginning a short overview of the agenda. After an introduction to Stackforce, I will provide you an overview of our OMS over LoRaWAN solution, followed by the description of a typical use case in the smart metering world. To complete my part of the webinar, I will present you our portfolio for OMS and LoRaWAN protocol stacks and give you a short description how you can get access to our stacks. Now, who is Stackforce anyhow? Stackforce is one of the leading experts in the development of embedded software in the area of wired and wireless connectivity technologies for various IoT applications. The main IoT applications where our stack is used are smart metering, smart sensoring for industrial, smart city, and smart farming use cases. The origin of Stackforce started already in 2002, but the focus for today is to provide you an impression about our expertise in wireless M-Bus, OMS, and LoRaWAN. The development of our first wireless M-Bus protocol stack started already in 2008, with the release of the first stack to the market 2 years later. In 2015, Stackforce was approached by Semtech for a joint development of the first LoRaWAN protocol stack, the well-known LoRa Mac node, which was released in 2016. Since then, we continue to extend our LoRaWAN portfolio by introducing in 2020 our first OMS plus LoRaWAN dual stack, followed by the OMS over LoRaWAN plus OMS dual stack in 2023. In 2025, we released the LoRaWAN single stack supporting also Class B and a Fuota module that can be used in combination, for example, with the LoRa Mac node. After this short introduction to Stackforce, I come now to the main topic of this webinar. As mentioned already, we have since 2023 a dual stack in our portfolio that supports OMS and OMS over LoRaWAN. The architecture of this stack has the advantage that it allows a seamless switching between the stacks. The switch between the stacks can be done during compile time, in the production, but also in the field. It therefore allows the maximum flexibility. for the users. The integration of fully standardized protocols, namely OMS and LoRaWAN, enables the end customer, the utilities, to be independent from a specific meter supplier. With the porting of OMS upper layers on top of the LoRaWAN layers, eases the integration of LoRaWAN into the OMS world. All our protocol stacks are pre-certified. In this case, with the related OMS conformance tests and the LCTT test for LoRaWAN on the reference hardware platform, which is the STM32WL5WLE5 from STMicroelectronics. On demand, we can also port the stack to other semiconductor platforms. This picture shall illustrate the structure of the combined stack. As you can see, the upper layers, AFL, TPL and APL, are the same for the wireless M-Bus and the OMS over LoRaWAN. Our stack architecture is designed in a way that these layers will be jointly used from both stacks. This ensures a minimum memory overhead. This overhead is coming from the M-Bus application layer according to the technical recommendations 06 that was introduced from the OMS group to enable the integration of LoRaWAN into the OMS world. To understand better the memory footprint, which I will present in the next slide, I would like to give you a short overview how our protocol stack will be delivered. The protocol stack itself will be provided in object code. But to ease the integration onto the targeted semiconductor platform, but also to accelerate the implementation of the stack into the overall software, we provide the application and a platform interface in source code. Our stack is also designed in a way that it can be used in 2-chip or 1-chip designs. Due to the optimized architecture, our memory footprint has very limited overhead, as already mentioned before. In the table, you can see the memory footprint for typical and for a full-fledged usage measured on our reference hardware from STMicroelectronics. The memory footprint can vary depending on the final configuration done by the customer. The memory consumption of the stack library is between 87 and 103 kilobyte, and for the flash between 9.2 and 11.4 kilobyte for RAM. The memory consumption for the other parts is between 26 and 28 kilobyte for flash and between 8.3 and 8.6 kilobyte for RAM. The question is now, how will the stack support the selection which communication technology will be used to transfer the data from the meter over the air? Assuming that the meter is communicating with OMS over LoRaWAN and there is a need to switch to OMS. In this case, the application only has to call the related API function and the stack will take care to switch to OMS. When the communication shall go back to OMS over LoRaWAN, again only the related API has to be done and the stack will switch accordingly. A typical application for such a dual stack is shown in this picture. The standard communication is done via a fixed network, in this example OMS over LoRaWAN. In case the meter realizes that the OMS over LoRaWAN communication is not received by the gateway, the meter can switch to the OMS communication as a fallback solution, allowing the utility to collect the data via walk-by or drive-by. As soon as the connection with OMS over LoRaWAN is possible again, the meter will switch back to the standard communication technology. How is it done was just presented in the slide before. Due to the fact that the LoRaWAN and the wireless M-Bus are using the OMS upper layer protocols, it makes it very easy for the utility that is normally used to work with OMS data to collect and work with the data in their head-end system. For them, it is transparent via which communication technology the data has been transported. For us, it is very important to work very closely with the main semiconductor vendors. We have installed related partnerships with NXP, Semtech, Silicon Labs, STMicroelectronics, and Texas Instruments to ensure the best possible solutions for our customers. For the wireless M-Bus, we have protocol stacks available for the end device and gateways, and as you can see, based on various semiconductor platforms. For the LoRaWAN, we are focusing on the stacks for end devices and offer solutions for single and dual stack applications. Focus is here on platforms from Semtech and STMicroelectronics. As mentioned already before, since beginning this year, we offer a module to support FOOTA that can be integrated into the LoRa MEC node. In 2026, we plan to support the relay functionality for end devices too. The final question is now how to get access to the stack to start testing it. We offer for all of our stacks a free of charge evaluation stack that can be tested for 180 days. It is in principle a full stack but has some technical limitations to prevent the usage for mass production. The process is easy and straightforward. The customer has to select a targeted stack and hardware combination. After that, he needs to sign the related evaluation agreement to be able to download the stack and start integration and testing. The related documentation is part of the downloaded file. This is the end of my presentation. Thank you for your attention, and I will hand over now to Olivier.
Okay, thank you all. So we've got a lot of information. I just want to wrap up quickly. So in the next slide, really, I'm sort of putting together the big picture. If you have a LoRaWAN network that is able to connect the meters, you can see here the meters top left, they will be communicating with the utility infrastructure or the region infrastructure. You know, more and more we have municipalities or regions that develop their own LoRa network for smart city type applications, including, of course, water metering or gas metering. But not all meters can be reached. And therefore, you also have these isolated meters here, bottom left. And that's where really M-Bus is so powerful, because these meters, as was explained by Stackforce, really, they can switch seamlessly between the LoRaWAN version of M-Bus and the traditional version of wireless M-Bus. So you can collect these radio frames, which go to a shorter range, and this is called drive-by. So you can see here, typically the equipment is put on garbage collection trucks. And as these trucks go around the city, they also do the secondary task of collecting the data on meters. But also, now we have another standard in the LoRa Alliance, which is called the battery-powered relay. So when you are aware about the device, you will start to see these relays in many places in cities. You know, typically it's a small box connected to a pole. It could be a street light lamp. And what these boxes do is they're able to receive communication from up to 15 meters around that relay. So typically in a city, this would be about 400 meters around the relay. And they will amplify the signal and send it to the main collection point. So that's now an alternative way of collecting isolated meters. The use of it on the next slide, Chansey, please. It's really cost optimization. The curve that you see on the top left is what happens traditionally from the economic point of view as you want to increase the penetration of the network towards 100% of the meters. So that's the x-axis. On the y-axis, you get the cost of the network. And the last 10% and the last 5% of the network, they cost a lot more than the first 5%. So at some point, it does not become rational to deploy a fully fixed network for the last 5% of the meters or so. And that's where you switch approach. And rather than densifying the network, the entire network to reach these meters, you have a more dedicated approach where you pinpoint where the hard-to-reach meters are, and you go collect these meters with relays. So that's the new approach in the LoRa Alliance. So be aware that because the relays are battery powered, they sniff the radio signals. So they sleep, wake up briefly to sniff for any incoming signal, sleep again. So when you transmit your packets to a relay, you need to implement a specific preamble protocol. So the LoRaWAN stack needs to send this additional protocol, but outside of this, the rest of the actual data transmission remains the normal LoRa payload. So this is particularly useful, of course, for water meters, which are typically in hard-to-reach locations. I just want to briefly, on the next slide, touch upon another new thing that still is being developed by the LoRa Alliance. And actually both Birdz and Actility and other meter vendors are collaborating there. There is no reason why the wireless M-Bus walk-by drive-by protocol could not leverage the long reach of LoRaWAN. So overall, the idea is that the meter will be able to discover that there is a mobile gateway somewhere in the vicinity through detecting a specific beacon of the gateway. And when it detects this beacon, it activates this walk-by drive-by mode and broadcasts the signal. So it will be very, very similar to what wireless M-Bus is specifying, but using the LoRa PHY layers and therefore extending the range. So stay tuned. This is not yet a standard. It will be in the future once the LoRa Alliance has nailed down all the details. With that, we've reached the end of this webinar. So we are switching now to the Q&A session. So feel free to ask any question to any of us, and we'll try to answer. Okay. I can see we have the first question on the range of wireless M-Bus. I think, Ahmed, you can address this one from your vast experience of wireless M-Bus.
Yes, thank you, Olivier. So regarding the range of wireless M-Bus, so mainly in the 868 megahertz bands, we have radio modes with a data rate up to 100 kilo chips per second. So this is a quite high data rate. So indeed, the range will not be that long. But typically, we could say that this is from tens of meters to hundreds of meters, depending on the radio propagation conditions. So if the meter is deep indoor, of course, this range will be decreased compared to a meter that is outdoor. But as mentioned before, wireless M-Bus in 868 megahertz band is mainly dedicated for walk-by, drive-by. So this is kind of neighborhood propagation. It's not meant to be used in long-range propagation. Sorry.
Maybe I just can add, Conrad speaking here. Sorry, my video is somehow not working. Wireless M is also a lot of used in submetering market in Europe, because you have the gateways always in the houses, in the stairways, and here wireless M-Bus is a pretty good technology for collecting the data from the submetering, heat cost allocators, water meters, and so on. So more indoor or in-house applications. Then you don't need a wide range of the distance, like for LoRaWAN, for example.
Thank you. And then we have a question that's, I think clearly for Stackforce. So Conrad, I guess.
I hand it over to Mario.
Yes, so the question is about how fast the device can switch from AMI to AMR. So that means from the fixed network connection to LoRaWAN and to the wireless M-Bus walk-by drive-by mode. And actually, it's always the decision of the application whether to switch or whether to use LoRaWAN transmissions or the wireless M-Bus for the uplink. And the switch time is as fast as the device can switch or between wireless M-Bus and LoRaWAN technically. So just needs to reconfigure the radio for the other operation, and then the application is free to go with either the other technology. And it can work in parallel, let's say, in the way that you can only have one stack active at a time, but you can switch them in the field on the device whenever it's necessary to take the other technology.
Thank you, Mario. I guess maybe you can address the next one. Mr. Gong is asking if it's possible to evaluate the Stackforce OMS Over LoRaWAN to apply for a testing license.
Yes, I can take this one. Yes, for sure, this is possible. As I mentioned before, we have for the stacks an free of charge evaluation license. It's valid for 180 days, has a little bit limitation that after every 20 transmission you have to reboot, and the payload is maximum 51 bytes. But from the experience of our customers, for testing is not a limitation. You just have to sign an evaluation license agreement, which you agree to the terms and conditions. Then you can download the stack. You get an email, you can download it, and you start to testing it. You have to ensure that you have the right hardware available. So we need to know which hardware, which platform you prefer. Then you get the stack for this dedicated platform.
Okay. And on the need for Actility server, so strictly speaking, to evaluate the OMS over LoRaWAN, you need a LoRaWAN network. It doesn't necessarily need to be Actility infrastructure. However, if you want to decode the OMS payload, you also need to have OMS decoder, so you can either interface your existing LoRaWAN infrastructure to device lab. So obviously, that's for this you can address Palle directly, or you want something that's pre-integrated. And indeed, as you've seen, we have pre-integrated that to the Actility network server. One thing that's important when you want to do an OMS over LoRaWAN, you need to really identify your meter. So we make sure ahead of time that everything has been tested and working fine. On the next one is on security key distribution. Well, I can talk about my experience, but maybe I think my colleagues can chime in. Most device vendors, when you buy the meters, they will actually create an account, and they know which meters you have acquired. From your account on the water meter, you will then be able to download a secure file with your keys. So far that has been my experience, but I think, I don't know if anyone wants to share their experience. It obviously depends on the meter vendor.
Absolutely. I would like to add to that, because the standards are quite precise about the key itself and the characteristics of the key. but it says nothing whatsoever on the delivery and logistics on the key. And it turns out that each meter manufacturer has found their own solution. And I think we have seen it all, ranging from one meter manufacturer decided to print the key on a small piece of paper and put it into the box, which was potentially the worst possible solution, and ranging onto the more modern solutions where you are assigned to an account on the website where you can download your keys in an encrypted format. But I think anything between is possible, and the standard is not requiring any specific things with regard to delivery.
On the LoRaWAN side, for those who are not aware, there is a secure key distribution mechanism that has been defined. You can, at production, put all your keys in the LoRa, so-called the LoRa joint server, which could actually belong to the meter manufacturer or belong to some partner. You're given a one-time activation code as part of the LoRa QR code, which unlocks the generation of keys at the joint server. So it's all a little bit complex to explain. But of course, this applies only to the LoRaWAN key, because you need to bear in mind that for LoRaWAN OMS meter, you will need two keys. You will need the LoRaWAN key and the OMS key. And the LoRaWAN part can be specified to be distributed in a very, very secure way. And OMS, it depends a little bit on every vendor.
And on top of that, Olivier, if I may add something regarding the OMS key that we call the master key. So there is an integrated security protocol enabling the utility and the meter manufacturers to update the key remotely. And this is explained in the OMS specification and also in the M-Bus standard using the security information transfer protocol.
Thank you, Ahmed. Two-way communication. So all the meters that I'm aware of, they use today class A, which means that at a very precise time after the uplink, so it can be 2 seconds, but actually it's tunable per network, you have a small slot to send a downlink. So when you want to send a command to any LoRaWAN class A device, it's the LoRa network server that will decide which command goes to which device, and it has the precise timing to do this. The capacity for commands is a lot lower than for uplinks, so that all LoRaWAN networks, they are imbalanced. You know, they have more capacity uplink than downlink, but clearly it is possible to send downlinks to multiple devices, whether it be valves or any other device that is unrelated to OMS. On the specification for bidirectional valves, I'm not the expert here. I don't know if anyone knows about valve control in OMS, if that has been specified already.
Yeah, I can take that one. So the OMS specification has an annex to the specification, which takes care of the definition for different use cases. And it also covers the valve control and defines the data points and commands that need to be exchanged to control the valve. It's the Annex M.
Mario, I think there is no question you cannot answer. What happens if the payload is more than 51 bytes and the device is using SF12? I think that's a segmentation question. And
yeah, I can take care of this one, Olivier. So indeed, this case is considered in the OMS Over LoRaWAN technical report. So there is a dedicated section for that. So indeed, in OMS and M-Bus, we have what we call the authentication and fragmentation layer. And this fragmentation layer could be used on top of LoRaWAN to manage the scenarios where we have payloads that could not be sent in one single LoRaWAN packet. And this could be used in a transparent manner, and the fragmentation layer implemented on both the end device, so the meter, and the headend system, take care of the fragmentation and the reassembly of the message on both sides.
Thanks, Ahmed. The next question was also related to segmentation, so we answered already. Availability on starter kits available for testing OMS over LoRaWAN. Nothing really shrink wrap, sorry, on the marketplace, but it's fairly easy to assemble yourself. I know, for example, in the demos that we worked together with Jakob, we worked with I think was Kamstrup meters that have OMS readily implemented, and they're available relatively easily. So I think you need to find your meters and then the rest of the OMS and LoRaWAN part can be provided relatively easily.
Yeah, if I may add a comment there, Olivier. Obviously, we do not supply hardware at all from Device Lab, but we can offer you our software on a test license, which is free of charge, which will cover 100 devices for 90 days to allow you to evaluate how it works. And it's fairly easy to integrate. Correct me if I'm wrong, Olivier. You have tried it, but it shouldn't take long to integrate it into your host system.
Indeed. On the next question, on average, how many readings are transmitted in a single uplink by OMS meters?
So it depends on the data encoding, on how many bytes you will use to encode a single reading or consumption index. But yeah, this is very implementation dependent. So you can encode, if, for instance, if you use 2 bytes or 4 bytes to encode your consumption index, you can send them more than 10 meter readings, for instance. But you have to keep in mind that you need also to send other information along with the meter index. You have to send information regarding battery status and regarding the alarms, etc., etc.
Last question on the list on compatibility of head-end systems, the HES with wireless M-Bus. Whether a non-OMS compliant wireless M-Bus will interpret an OMS compliant meter payload. I think the subtlety might be on the security side. Maybe I don't know if you want to comment on your experience with head-end systems that are used to wireless M-Bus, whether they would accept OMS. The issue, I think, is there are many options in wireless M-Bus, and OMS will actually specify some of these options that might or might not be supported by your existing wireless M-Bus system. I don't know if someone has more specific comments.
I can add to that we actually have a customer using our software totally in parallel with their own in-house developed decoder. Obviously, they need to have a separation mechanism to decide which decoder should handle a specific datagram. Also, we have prepared a custom output format for them. But apart from that, they work totally independent and parallel.
Yeah. I would say on our side, the main subtlety we found compared to non-OMS meters is the need to memorize state for OMS, because there is a certain number of, there are information that are exchanged at setup time, at commissioning time, that will not be provided later on by the meter. So your driver needs to have some memory. But apart from that, as Jakob said, the integration was pretty straightforward. Okay. That's all for the questions today. So thanks everyone. Thanks to all the speakers and for all the expertise.
Exactly, Olivier. There is one more question.
Oops, it keep coming. Sorry. FOTA was mentioned, how it works. So FOTA is there are actually two FOTAs. There is a FOTA that is specified on the wireless M-Bus layer directly, so that you can use, for example, as part of drive-by. And there is a FOTA defined at the LoRa Alliance level, which supports also multicast. So maybe we can address first the wireless M-Bus FOTA, I guess from your expertise, and then maybe I can be more specific on the LoRaWAN FOTA.
Yeah, I can elaborate a bit on that. So indeed, we have the firmware image transfer feature in the M-Bus protocol. And with this, we can use the fragmentation layer as mentioned before. So we can transport all the firmware over LoRaWAN, over the LoRaWAN link layer, and the M-Bus application layer will handle the firmware image, and the fragmentation layer will handle as well the reassembly of the message.
So that's the first way to do FOTA. That's what's available on most meters today. So if you want to do firmware update today, practically this is your only option. However, there are many vendors that are now implementing in parallel the LoRaWAN FOTA, which is based on multicast. So it's really interesting because obviously radio is natively multicast, broadcast, as the name implies. So what you do is you take a given firmware, you add forward error correction data. So you would actually triple or quadruple the size of the initial firmware, and you broadcast it. The meters will one by one tell you whether they have received that firmware. And the whole thing is called a campaign in LoRaWAN. To make it work in practice, so this is all specified by the standard. What is not specified by the standard is whether you will support firmware compression. What I recommend people to do for industrial implementation is to compress the firmware update. So it's a sort of delta compression of firmware, which is not easy. You know, when you think of it, there are pointers in your code. It's not as easy as just you know, doing a subtraction of code or whatever. You need to take into account the changes of pointers when you apply a patch. But you can do about 90–95% compression on a firmware using delta compression. You can select your own mechanism for delta compression, and that will make multicast firmware update quite usable, because then of course the information you need to relay is a lot less than what you would without such compression. So I think that was the last question. So thanks again, everyone. We are past the hour, but that shows a lot of interest in metering and OMS metering. So that's promising.
Thank
Bye,
you.
everyone.
Thank you, Olivier. Goodbye.
Thank you. Take care.
Bye.
Bye.